Thank you for inviting me. Like Tony said, my name is C.Siefert, and I'm from Sandia National Labs in scenic Albuquerque, New Mexico. And I'm here to talk today about Trilinos. And so it's different from PETSI, as he expressed earlier. There's some overlapping capabilities. There's something PETSI does that Trilinos doesn't do. There's things that Trilinos does that PETSI doesn't do. And I'll try to walk you through what features Trilinos has that might be useful for you in the problems that you're interested in solving. So by the time I'm finished, I'd like to kind of answer these questions. What can Trilinos do for you? In some sense, that's the most important question. Otherwise, you wouldn't be here. How the software is organized. Give you a brief tour of what packages Trilinos has available. Talk about how do I get started effectively. And then do a little bit of preparation for the hands-on tutorial this afternoon. So what can Trilinos do for you? Well, it's a C++ predominantly object-oriented software framework. And it's designed to solve large-scale science and engineering problems. And the analogy we like to use is it's more like Lego than MATLAB. MATLAB, everything's all right there for you. Lego, you have every piece you need. You're just going to have to put it together yourself. And so that's kind of one of the analogies we like to use to describe Trilinos, where all the various different packages might be different bricks in that brick pile. We have a lot of people who've worked on it, and this is just a sampling of names. I know there's a bunch that are missing. Most of these folks are or have been at Sandia at some point, but there's plenty of people who are at Oak Ridge or university collaborators across the United States and across the globe, as well as folks who've been contributors to Trilinos and then moved on to other things. So it's a large set of software, a lot of people that work on it. Its sort of core in history is solving large-scale PDEs. That's kind of where Trilinos came from, dealing with, effectively at first, the linear algebra and the linear solvers, then branching out more into other things you would need to do that, discretizations, et cetera. Circuit problems are another area that Trilinos has historically made a lot of impact. At Sandia, we have a circuit solver called Zeiss, which works similarly to SPICE for anyone who's familiar with that code, only it's designed for high-scale parallel computing, and Trilinos is a core reason of why it can do that. And there's plenty more PDE problems. So what did we actually stick in here? So there's obviously some kind of a fluid flow problem. This is a magnetics problem. There's some kind of atomistic particle problem there that we stuck a little picture of as well. That's magnetics. And I have no idea where that one comes from. But there's all sorts of different things we've used it for, so much so that it's hard for anyone to have a snapshot as to everything Trilinos has been used for at any point in time. So we do a lot of structural mechanics, circuit simulations, electromagnetics and plasmas, combustion and flow. We also look at coupled and multi-physics problems, not just a single physics at a time. And then we actually have some people who use it for data and graph analysis. I don't know where the even gaming comment came from, but there's always been rumors that someone's managed to use Trilinos for something in some game project at some point in time. I have no actual confirmation as to what that is, but I keep on hearing it. The goal for what we want to use Trilinos on is everything. And by everything, I mean laptop, like the ones you have sitting in front of you, workstations on your desk, but scaling up to the largest computers in the world. Both kind of the computers we have today and the computers ideally we'll have tomorrow. So like our multi-core CPU, some of the machines that have GPUs on there where you want to actually use it for solving physics problems rather than doing graphics. Being able to work, kind of MPI is the core way we work, but also be able to support all sorts of threading models, OpenMB, Intel's thread building blocks, pthreads, and then all your GPU programming models and combinations thereof. In a sense, the combinations thereof part is slightly more of an aspiration than a reality, but we're moving to get there. Primarily, it works all in C++. That's where most of our code is written. But we have skins for Trilinos as well. So we have interfaces in C, Fortran 2003, Python, and then for our hands-on tutorial, we have Web Trilinos, which is basically like a web interface to basically play around with, showing you how it works that we use for demos. I wouldn't use it for anything substantial or real, but it's good for these sorts of things. What makes Trilinos unique? Well, it's a huge library of algorithms, and I'll go through more of what that can do later as we get to the packages. But there's a list of things and pieces, and we'll go through more detail about that. We also have a growing support for multi-core and hybrid CPU-GPU algorithms. The idea being that it's all built in sort of under the hood, and so your application code doesn't really have to think about it too much, so long as what your application code is primarily doing is sending things to Trilinos. That you can just kind of recompile it on a GPU, and it will work reasonably well. With the goal of basically being able to take this and take your whole stack and just have it work. Again, slightly more of an aspiration than a reality, but that's the direction we're heading in. Likewise, mixed and arbitrary precisions. So sometimes you want to solve a gargantuan problem, say more than 2 billion unknowns. That's where you hit 2.1 billion is where you hit the largest integer with 32-bit in. And sometimes you really want to solve a problem bigger than that. I don't know how many graduate students want to solve problems that large, but certainly at the labs we have people who are interested in problems that gargantuan. And so we've got the ability to basically handle these really large problems, but also to do, say, higher precision. Some folks are interested in solving with quad double, which for many things is completely excessive, but for some problems you really do need that extra accuracy. And likewise, mixed precision algorithms. So doing some computations in float and others in double, say, or some in double and others in quad double. For GPUs that are slightly older, that have really bad double performance, being able to do things in float is a real advantage. Or likewise, sometimes you really want to do higher precision accumulation, and you want to do certain calculations, say, in quad double. And the goal would be able to support all of these sorts of things in a fashion that's reasonably straightforward to follow and actually usable. So where did Trilinos come from? So here's the baby picture, as it were. It started as linear algebra distributed objects, ways of taking matrices and vectors and spreading them across a large parallel, at that point, MPI machine. We added linear solvers to that. And then kind of as time went on, different stuff started accreting to Trilinos. He said, oh, well, it would be really nice if we had, say, discretizations for like finite differences or finite elements. So we added some of those. Or maybe it'd be really great if we could do time discretization. And so that came in. Or maybe it'd be great if we supported like automatic differentiation. Because sometimes writing a Jacobian of a nonlinear system is really hard to do by hand. Or domain decomposition, Mortar methods, optimization, etc. Support utilities like load balancing. And they've all sort of, come in over time. What started as a small handful of packages, probably somewhere in the 10 to 12 range, now looks something more like 60. Kind of building up from the start of linear algebra, linear solvers, all the way up to the present where we have space and time discretization, optimization, sensitivity analysis, and uncertainty quantification, kind of filling out the whole stack of things that people might want to do with like a large-scale PDE problem. And so another way to look at this and sort of I think the optimization guys kind of like this because it puts them all the way at the top of the heap. But you can look at it effectively as building up a simulation capability, starting with your forward analysis, your matrices, your linear algebra, talking about accuracy, better discretization, sensitivity analysis, optimization, uncertainty, et cetera, pushing up towards effectively what I call a decision support model. At the end of the day, somebody wants to build something or do something. Can we give them an answer with an uncertainty, a margin of uncertainty that they can use to decide whether or not I want to do X or Y? And so kind of at each stage, computational cost gets larger. And so the whole idea of this is all of our methods should be scalable to be able to address those issues. And so that's kind of what we shoot for. So strategic goals, scalable computations for the reasons I just explained. Hardened computations. We use the word hardened instead of robust because if you're a statistician, robust has a very particular meaning. And that's not something I want to directly imply here. But the whole idea is you should only really fail if the problem's intractable. And then the failures should actually have useful messages. And likewise, have full vertical coverage from the problem construction, solution, analysis, and optimization. From a software perspective, the two kind of goals are universal interoperability and accessibility. Interoperability, we should work well within Trilinos, but also with external software. So PETSI specifically, Hyper, which you'll hear about tomorrow, but also, for instance, all the other tools in the X toolkit. And then from an accessibility perspective, being able to use various programming languages, so that's why we have our skins in C and Fortran and Python. It should run on basically any hardware, including some of the crazy CPU, GPU machines that people build these days, and likewise support a variety of operating systems. So I usually run Trilinos on Linux. Plenty of other people do Mac OS, but we also have a reasonably good support for Windows, for folks who want to do high-performance computing on Windows. That's an option available as well. So that's kind of what we shoot for. So what do we actually have, and how is it organized? So like I said before, Lego, not MATLAB. And so Trilinos' kind of atomic unit is a package. We've got like 60 odd of those. Each one's going to have its own development team, usually a small handful of people. You know, it might be 5 or 6, it might be 3 or 4, it depends on what package it is. Each package is going to make its own decisions about algorithms, coding style, et cetera, and where it makes sense to build dependencies on other Trilinos packages, both required dependencies and optional ones. And so the nice thing about this is Trilinos is not an individual monolithic framework set up where you have to use all of Trilinos or nothing. You can pick and choose kind of what you want and pick the capabilities that you're interested in. So when I was a graduate student, I needed a multigrid method. And so what I wound up doing was taking just the parts of Trilinos that I needed to use multigrid for my particular problem in structural mechanics. And that's all I took. Linear algebra, multigrid. I didn't look at the discretization because I already had one. I didn't do optimization because I was only interested in a forward problem. I just took the pieces I wanted. And it worked actually really well for me. And this is long before I actually was working at Sandia or anything. It was something that I came to from sort of an outside perspective and managed to make work for what I had. There are always new packages under development, very few of which I'll talk about today, but we're always kind of adding new ideas and new algorithms. The top layer framework is basically a small amount of code that manages all the package dependencies and gives us a test system, et cetera. So the reason we do this is effectively so each team can kind of do what they're doing without being tied down too much from the top. So if I'm on the sort of multigrid algorithms team, which I am now, I can work on that without worrying what the optimization guys are doing or without worrying what, say, the load balancing people are doing. Each person can work in their own sort of area. In terms of interoperability, we strive for can use rather than depends on. To minimize the amount of Trilinos you have to use if you just really want one piece. But allow them to use things where it makes sense. So for instance, our nonlinear solver, Knox, needs to solve linear systems. If you think about Newton's method, you have to solve a linear system at each step. And so we can use any of our kind of linear solvers, so Aztec or Bayless, or we can use LAPACK. For instance, if our problem happens to be dense, LAPACK's the right way to do that. Likewise, our linear solver, say Bayless, needs preconditioners and it needs matrices and vectors. So it can use any of the things we have under the hood, so Petra, Petra, or it can use PETSI. And they can use any of our preconditioners that we have in Trilinos, or it could use something else. Sometimes the right thing to do is effectively to have a very problem-specific preconditioner that you've already implemented. And so we can accommodate that. And then effectively, when you select all this interoperability is when you configure Trilinos. You say, OK, here's what I want to turn on. As I'm turning stuff on, it'll basically pick out what can use what and turn on all those various dependencies accordingly. And so we use CMake, which is a sort of build system that's not quite as common as AutoTools, but provides some nice functionalities, primarily like allowing us to build on Windows machines, which is something we'd never be able to do well using AutoTools. So we can kind of break up our ideas and capabilities kind of by area. And that's how we've chosen to sort of loosely organize ourselves. And there's a bunch of names there describing who the capability leads are. If you know any of these people, this might mean something to you. If not, you've got the slides, so this should be kind of a reference for if you had a first-line question, who might be able to answer it. So there's the framework on top, which is basically the build system, the testing system, all the stuff that allows us to kind of do good software engineering. There's the software engineering technologies and integration, kind of developing new ideas for how to better improve software quality. Discretizations in space and time. Geometry meshing and load balancing. Effectively, that includes both mesh generation, combinatorial scientific computing problems. So zoltan would be in this category. You'll hear more about that one tomorrow from Eric Billman. But also, say, mesh smoothing and those sorts of things. Scalable linear algebra, so that's the kind of core matrix vector representation, as opposed to linear and eigensolvers, which I'll spend a large amount of time talking about today. Nonlinear transient optimization. And then finally, our last one, and the newest, is scalable I/O. With the idea being that, on a sufficiently large system, input and output, if you don't think about it well, can actually soak up a non-trivial amount of time. I know as a linear algebraist, I don't normally think of, I'm like, oh, just printf that to screen, whatever, that'll work fine, or dump this out to disk, I don't really care. But if you're on a really big problem, taking sort of a lazy attitude toward that can really hurt you in performance. And so having a good I/O system can actually make a difference. And so there's multiple packages in each area. Alrighty. So let's kind of walk through that. Let's start off with effectively what we'll call the solver stack. So we'll start off with representing matrices and vectors. That's kind of how we have to start. And being able to compute things like vector additions, maybe scaled, matrix vector multiplies, that sort of stuff. And so the kind of two core areas to do that are epetra and tpetra, but there's also cocos, which is how we do node level parallelism, so like on a GPU or on a multi-core node with threads. That's kind of the bottom building block we have. From there, then we might want to solve a linear system, right? We built a linear system. We'd like to be able to solve that. And so the idea to do that would, say, be able to do, say, a Krylov method for either the linear problem or also the eigen problem, for that matter. And we've got kind of a set of Krylov methods, a set of preconditioners, and then a final Anisazi, which is an eigensolver package. If I've solved the linear problem, maybe my problem's really nonlinear. I would like to actually solve a nonlinear problem that the linear problem just is some subproblem of. So there we have Knox to do that. Maybe I want to do time integration because some problems are transient. So I want to have a time integration capability, and so that's where Rhythmos falls in. Basically, the way I think about Rhythmos is doing sort of, time integration forward in time, but in effect, it's a general DAE solver that you could use to do whatever you want appropriately. Say I'm feeling a little bit more avant-garde. I want to do a bifurcation analysis. We have that capability in Loca. Or finally, maybe I want to do optimization, right? I've built my nonlinear transient forward problem. I want to pick the right parameters to deliver performance I want. Being able to do, say, solve an optimization problem with Mucho. And then finally, to be able to do sensitivity analysis kind of across the board. And the key enabling technology there, which I'll go into some detail on later, is automatic differentiation for C++ via Staccato. So here's a better picture, kind of by capability. So we have a number of different meshing packages. Some of those are real packages in Trilinos, say like PamGen or STK Mesh. But there's also interface to the ITAPS interface for folks who are familiar with meshing. That's a kind of community interface to meshing and load balancing, and so we support that as well. There's mesh smoothing via Mesquite. Probably my favorite one out of that batch is PamGen, which is basically for parallel inline mesh generation. You write a simple set of statements which specifies, hey, I want to mesh. I want to, for a simple geometric object, I want to distort it in this way, and it can generate a mesh for you on the fly rather than having to read it off disk. So that's really useful for scalability testing, because usually for a scalability test, you want a relatively simple mesh, but you just want it to be really big. So PamGen enables us to do that. Time integration with Rhythmos, which I mentioned. Automatic differentiation, Staccato. We'll talk about that in more detail. That's actually really cool. Mortar methods. They're common. Subsurface flow people really like them. Some structural mechanics guys like those. We have some capability via Mortel to do that. Core linear algebra, epetra, tpetra, and cocos. Interfaces for linear algebra. That's sort of a interesting way to express that. Part of it is interfaces to allow easy assembly from finite element problems. That's the FEI. Or unified interfaces to solvers. That's Stratamicos. Load balancing, again, you'll hear more about Zoltan tomorrow. Your various skins for your Python, the Web Trilinos, the Fortran, the C. And then Optica, which is a way for manipulating kind of input parameters graphically. Effectively, you've got the ability to specify everything through a kind of parameter list, a list of options that you can store separately in a text file and then change it without having to recompile Trilinos. And Optica is a way to interface that kind of in a GUI-like interface. Finally, support utilities effectively for all those various things. We have 3 families of iterative linear solvers, kind of Aztec, MO, and Bayless, which are Krylov methods, and then complex, which is real equivalent forms for complex valued problems. Bayless can do complex valued problems directly, but sometimes folks like to do real equivalent forms, so we have some capability to do that. Direct sparse linear solvers. We have, in this case, there's a Tim Davis's KLU is kind of built in, but that's also where we interface to things like SuperLU, or say MUMPS or Ifpac. If there's a third-party sparse direct solver that works well for your problem, chances are we have an interface to that through Trilinos. We have some dense direct solvers. Most of that is LAPAC interfaces, in effect. Iterative eigenvalue solvers, preconditioners of several flavors, both ILU-type preconditioners, so incomplete factorizations. Again, we have an interface to the SuperLU incomplete factorization in there as well. Multi-level preconditioners and block preconditioners, also in that family. Some nonlinear solvers, optimization and sensitivity analysis. And then finally, some capability to do stochastic partial differential equations, which is relatively new, kind of avant-garde sort of stuff. Alrighty, there you go. There's the fast version. Now it's time to go into a little bit more detail. So there's a lot of material here, and they give me 2 hours to stand up in front of you. So please, if there's anything you want to know more about, stop me. Okay? I understand it's the 3rd day of this. But if you have any questions, that's really what I'm here for, is to help you be able to solve your problems, whatever they happen to be. So stop me as I go, if there's a particular package that's of interest. So I'll start off with discretizations, because that's usually kind of one of the first decisions you make. So we already have some software called Intrepid. And one of the key things about Intrepid is support for compatible discretizations. So a quick show of hands. Who's ever heard of a compatible or mimetic discretization before? All right, we got 1 or 2 in the front. That's actually more than I thought. So you can use Intrepid to do, say, your standard nodal finite elements of any order you want. First order, quadratic, cubic, all the way up to 10th order, if you like. But it also allows us to do methods on other topological entities. So it allows us to do, say, edge element basis functions, so Nedelec elements, Whitney forms. That's really useful for magnetics. We can do face element basis functions, which have all sorts of values. If you think about like staggered discretization, sometimes you get something that has a face-like feel to it, etc. You can do standard shapes, all your tets, your hexes, your quads, your tris, but also arbitrary polyhedra. There's some very nice capability in that if you're into sort of polyhedra or polygonal elements. You can do finite difference, volume, or element calculations. And one of the nice things about this is the way it's all built is to enable some of this uncertainty quantification that we could use later via Staccato. So you can actually differentiate automatically through all of this. So if you have a material parameter that you're interested in finding out, say, sensitivities about, you can actually have it differentiate through this using our automatic differentiation capability all the way through the discretization, which is quite nice. There's a kind of map for how that works. If you understand discretizations and assembly at a deep level, that'll probably make sense to you. If not, the fast version is basically it's a framework and infrastructure to assemble these systems that has a lot of generality to it and supports basically everything you'd want to do in terms of discretizing in the class of finite element difference and volume methods. Yes?
Do you support C1 continuity elements?
Absolutely. Yes.
And can they be tweaked?
What?
Can they be tweaked? Can we go inside?
Well, so it's open source, so you can tweak anything you want. In terms of tweaking, what sort of tweaking are you looking?
The basis function a bit.
Yeah, well, you'd have to basically modify the code to do that, but there's no reason you couldn't. Let's say there's something specific you want to change. That's certainly doable.
Like I want to bring, let's say want to bring some physics that you couple with mechanics.
Sure, absolutely. You should be able to, I mean, you'll have to go into some code to edit that. If you're just wanting to bring in, say, material parameters, that's actually easier. You don't need to touch Intrepid proper. Even if it's a nonlinear material model, basically you're going to have effectively a set of Gauss points, and then you're going to evaluate your material state at all those points, and then you basically just hand Intrepid a vector and saying, here you go, that's my material state at all these Gauss points. Go ye forth and continue your assembly, and that'll just work right through. If you actually do want to change the basis functions a bit, and change how they work and how they look, that will actually take some modification, but it can be done.
Where can I get this information?
On Intrepid, so I probably should have stuck this up first. So trilinos.sandia.gov is our website. And that links to documentation on all of our Trilinos packages. So if there's something there, I wish we had a better way of mapping names to ideas, because they're listed all by name on the website. So if you know Intrepid happens to be discretizations, you're like, well, obviously this is where I look. But if you don't, you're like, well, I want to do discretizations. What do I choose? And so in this case, it's Intrepid. So if you have any further questions, we can kind of talk in more detail about that later. Any other Intrepid questions? All right, Rhythmos, time integration. If you're interested in effectively time integration of those sorts of flavors, we support it. So forward and backward Euler are the kind of obvious ones. There's Runge-Kutta of at least 4th order, maybe higher. I don't recall off the top of my head. Implicit BDF. Designed effectively to allow you to support operator split methods. So for instance, people who do shock problems are going to basically be using explicit time stepping for most of their things, in which case operator splitting is a perfectly reasonable thing to do. And so Rhythmos kind of is built to make that relatively straightforward, to allow each kind of operator to specify effectively what its CFL limit is and work through that. It's built, set up to do forward sensitivities. We're working on adjunct sensitivities. So if you want to do sensitivity analysis, Rhythmos, at least at moment, one direction, you're set. Adjoints are in progress to be able to work through that. Alrighty, that's kind of the quick tour of discretizations. I could go into detail about the meshing stuff, but I think it's a little more obvious. Automatic differentiation. This is one of the sort of cool and unique capabilities we have in Trilinos. So many packages in Trilinos have what I'll call fake Greek names. So like Trilinos is fake Greek for string of pearls. If you actually talk to anyone from Greece, they'll sort of cringe a bit about how we butcher their language. But staccato is fake Spanish. It's fake Spanish for I will derive. And so the idea of this is to basically provide automatic differentiation in C++. So who's familiar with automatic differentiation as an idea? All right, most people have heard of it. The classic way you would do this is you would use a source transformation tool. And this is just all about applying the chain rule. Now, I can do that by hand. Or I can go to like Maple or Mathematica and get them to do it for me. And then I have to either have it output code or copy it from Maple or Mathematica to my C++ or C or whatnot. Automatic differentiation takes a function in, say, C, C++, or Fortran, and then creates a function that evaluates its derivative. Traditionally, through like Ada4 or Ada-C, this was done through source transformation. You put in a function, you run this program on it, and then it spits out another function that evaluates the derivatives. Staccato does something different because it's looking at C++. And the way it works is using C++ templates, or abusing C++ templates might be a better way to put it. So the interesting thing about this is there's one templated code base. You don't have a copy of your function that does the function and then another copy that does the derivative. Because in that case, if you change the function evaluation and you forget to change the derivative, now these two things are out of sync. You have one templated function that basically has a staccato data type that it can template on that can basically push the automatic differentiation through. Why would you do this? Well, Jacobians for nonlinear iteration is sort of the most obvious. If I have a multiphysics code or a code where I have lots of different material models, say, I might want to turn one on or turn one off or turn one on here and have a different one here. That's a lot of code to write by hand to maintain and ensure correctness. The idea of Staccato is to be able to minimize the amount of pain and suffering on the behalf of the developer to be able to support that. In addition to just Jacobians for a nonlinear problem, this can also give you sensitivity and uncertainty quantification. If there are uncertain parameters, you can push those through the derivatives, et cetera, that you're computing for your PDE. One of the things I like about Staccato is doing manufactured solutions for verification purposes. So if I have a problem, I wrote up a code, I think it's good, how do I know it's right? Well, verification is an obvious way to do that. I create a solution, and then I say, OK, can I converge to the solution at the accuracy I expect? To be able to plug that into my problem, I'm often going to need to take some derivatives and create a right-hand side term. What do I normally do? Well, I normally pop open Maple or Mathematica, type it all in, hope I didn't make any mistakes, let it compute the derivatives, take that, rewrite it all in C++, plug it in, and hope I didn't type anything wrong again. Well, you can actually use Staccato. Its sort of lowest level use case is to be able to do that for you. Here's my solution. Figure out what my right-hand side is supposed to be. Yeah?
How do you provide that the curvature that you will use for the verification purpose will be the same as you use the solution?
Not necessarily. In terms of how you integrate. So what Intrepid can let you do is specify the integration of your choice, like how many points you wish to use. So quite clearly, you need higher order integration to do verification than you do to solve your problem. Otherwise, if you're trying to use the same set of points, bogus things can happen. So in terms of writing your functions that are going to say compute your error, when you go back to Intrepid, you can tell it to use however many, up to some level, however many quadrature points you want. And so for your problem, let's say you need just 2 points per dimension. For your verification, you might want to do 3. You basically just tell Intrepid, hey, I need you to use more quadrature points when doing the integration there to do that particular integration of evaluating the error. Straightforward enough to do. For folks who get excited about this, there's basically a bunch of different modes that you can do this in, forward or reverse, depending on how you want to deal with it. There's also a Taylor polynomial expansion as well. And then you can combine for higher derivatives if you need, say, if you're solving some fourth order PDE, you can make that all work. It's a pretty neat bit of software in that regard. All right. In terms of the core, if you're going to use Trilinos, this is the part of the lecture you're going to probably need to pay the most attention to once I get to effectively how our matrix and data structures are laid out. Tethos is actually just a utility package. What does that do for us? It provides parameter lists, which I'll talk more about later, which are kind of a way of telling Trilinos things in a nested fashion. It's got interfaces to BLAS and LAPACK that are also templated on an ordinal and scalar type. So you can do floats, doubles, et cetera, so long as you have a LAPACK or BLAS build that supports that particular flavor of math. We have a unified way to access it. Again, dense matrix and vector support, memory management, statistics, et cetera. And basically, it uses those kind of advanced C++ features. The common language for linear algebra is something we call petra. So I mentioned before there's an E petra or a T petra. There may be more petras later as programming languages evolve. Again, in our fake Greek theme, petra or rock. And so that's kind of how we represent our common linear algebra objects, at least conceptually. So what that would actually look like, effectively, is one of these two things. So E petra is our essential petra. That's our kind of workhorse implementation of this. It's sort of circa 2000 implementation, real double precision, C and Fortran interfaces. That's what gets used 99% of the time, because it's kind of our production capability. This templated petra is our kind of exciting next generation version. Here we're using basically decade-old C++. This uses effectively much more modern C++ techniques. Specifically to get at this, arbitrary scalar index type. So what floating point do you want? What integer types do you want to be able to support all those? Your floating point number, do you want that to be complex? We can do that, right? Do I want to do mixed precision? The other nice thing about this is it allows us to create effectively what we'll call node level support for these kind of hybrid architectures to be able to do GPUs, et cetera, without having to change your top level linear algebra code. Zoltan you'll hear a lot more about tomorrow. But basically, the way I like to think of Zoltan is Trilinos' one-stop shop for combinatorial scientific computing. That means load balancing, static or dynamic, take your pick, graph coloring, data migration. Once I've rebalanced my load, I want to be able to move stuff, and matrix ordering kind of services. So where this normally gets used, for instance, is partitioning, sort of the obvious load balancing case, either sort of statically at the start of a calculation or also during a calculation. So I do multi-level methods. On each level, I'm going to want to, say, rebalance my data to make sure it's still equally partitioned. And so Zoltan provides the ability to do that. And so it has both geometric methods that are coordinate-based. They tend to be really quick. But it also has kind of graph and hypergraph methods that are connectivity-based for cases where I don't have coordinates. So if I'm solving some structural mechanics problem, I know where everything is in space. If I'm doing data mining, I don't know what space really means. I don't know where those variables correspond to. I need a graph algorithm to do that. And as you might note, it also provides utilities, interfaces to external utilities. So for instance, Pato that Umut Shadel-Jurek works on, or Metis, Parmenas, Jostle, et cetera. And there's a specialized interface just for ePetra. Again, I'm not going to belabor this. There's plenty about Zoltan tomorrow. The final kind of bit of this is thera, which is effectively an abstract interface to linear algebra. The neat thing about that is it lets you compose operators in a fashion that works reasonably well. So I have a matrix, and I want to operate on some diagonal scaling thereof, or I want to block scale it, or I want to do something to it without like effectively restoring it. Thera kind of lets me do that. Then I could use a sort of concrete solver under the hood to access it. It's a neat capability, a little tricky to use. And then I also have our kind of skins. So I don't know how many people use Python, but there's evidently enough people that we have a Python interface to Trilinos. So basically, you build the Trilinos under the hood. And there's wrappers to kind of your linear solver stack plus Nox and Locus, so your nonlinear solvers as well, all generated via Swig. C Trilinos and 4 Trilinos are kind of handwritten interfaces. And finally, our Web Trilinos interface, which we'll see more of in the tutorial. OK, solvers. This is our kind of last bit of walking through packages one by one. Kind of my favorite bit, because that's what I do research-wise. So Amisos to start, sparse direct methods. KLU by Tim Davis built into it. And then the sparse direct solver of your choice, your SuperLU, Ifpac, Mumps, Scalapack, what have you. Interfaces to all of them so you can use them with Trilinos objects. So what this really gives you is a single consistent interface between all of them. So if I'm developing a code and I'm like, well, I know I'm going to have a sparse direct solve, I don't know which sparse direct solver works best for my problem. So I could go and write an interface for SuperLU, and an interface for Ifpac, and an interface for Mumps. And when I was in graduate school, that's actually what I did. I wrote interfaces for each one using their own peculiar data structures. Or I could use Amisos, basically, to allow me to try them all each one by one until I find the one that's going to work best for my problem, kind of allowing me to take care of it. The nice thing about it is it also builds in data redistribution under the hood. So if my code is parallel, but I want to try a serial direct solver, say because my problem is really small, so like regular SuperLU as opposed to SuperLU dist, it'll take care of the data migration for me. I'll build a matrix on partition between processors, and I say Amisos solve that. It'll condense to one, call serial SuperLU, and then propagate the answer back. There's a sequel to Amisos, Amethyst II, which is basically taking the capabilities we have in Amisos, but again, focusing on this arbitrary mixed precision, scalar type, hybrid discretization sort of capability. It was just released in Trilinos 10.8, so that would have been last fall, with some of these capabilities in there. It's still under development, pushing it forward to where it can deliver that in a sort of what word am I looking for? In a complete form. Aztec 00. This is probably the original Aztec. It's probably about 15 years old at this point. Developed in the mid-90s from MP Salsa. Probably one of the most widely externally used individual bits of software that we've done at Trilinos. Basically, it's a set of Krylov methods. So the obvious ones, CG, GMRes, by CG SAB, et cetera, but also some incomplete factorization preconditioners. And we've been using this for eons. More recently, there's this Aztec 00 interface, which basically takes the original Aztec code, which is all in C, and marries it to petra. So now I can use the standard objects that Trilinos provides, allowing us to use everything Aztec has, but also allowing it to work well with the rest of Trilinos, in the sense of we want to be able to work with other Trilinos packages when we can. So now we can use Ifpac and ML and other things I'll go into more detail about. Bayless is sort of the sequel to Aztec 00. So it has this decoupling from the linear algebra objects. So you can actually run Bayless using PETC linear algebra objects under the hood, if you so desire. And again, this is kind of essential so we can support all these kind of crazy CPU, GPU, advanced architecture things. But it adds some new functionality in addition to divorcing itself slightly more from the linear algebra implementation. For these two specifically, multiple right-hand sides, so that's block solvers. So the idea in that case is, OK, I need to solve multiple problems at the same time that all have the same matrix. Being able to handle that with a block Krylov method actually is a potentially fairly substantial win from efficiency perspective. The second is sequences of related systems. These are kind of Krylov recycling techniques, if you're familiar with those. The whole idea of that is I have a small perturbation to, say, my right-hand side or maybe my matrix. This sort of thing shows up in, say, a nonlinear iteration, perhaps, or perhaps more commonly into a transient linear problem, where there's going to be small perturbations each way. And these recycling solvers store some information out of the Krylov space to use it next time. So the whole idea is to accelerate convergence by saving some information from the last time because they're pretty close to each other. And so that's kind of some of the neat stuff that's not in Aztec that's kind of only in Bayless, so these recycling and block methods. There's also block orthogonalizations and seed solvers as well. And again, arbitrary mixed precision, complex, et cetera, which is kind of exciting because especially in like the realm of electromagnetics, say, there's folks who are really interested in solving complex valued problems, which Trilinos historically hasn't provided great support for, and so Bayless enables us to do that. Ifpac is our algebraic preconditioning. So it has two kind of key sets of operations. So first is Schwartz preconditioners, providing sort of an arbitrary Schwartz framework to allow us to do, say, overlapping methods on each core, or overlapping methods between nodes on a multi-core CPU. And we add that with effectively your sort of standard fixed point method. So there's incomplete factorizations, both of the ILU and ILUT variety. Relaxation, like a Jacobi or a Gauss-Seidel or a Chebyshev iteration, both in point and block form. And then also it's got some capability for block direct solves as well. And this effectively can be used. It uses petra under the hood, and it can be used with a bunch of other capabilities as well. So usually I use this as to generate smoothers for a multi-level method. It works quite well for that. Much how Amisos had a sequel, Ifpac II Ifpac also has a sequel. Ifpac II, again, this is supposed to exploit this advanced architecture framework. It's got a much, much better ILUT. 60 times faster than the one in Ifpac. We went back and rewrote the one in Ifpac afterwards, so they're about the same now. But again, to provide effectively this arbitrary precision advanced architecture support. ML is our multi-level preconditioning package. It has a sequel as well, but I won't go into detail about that today. It primarily provides smooth aggregation algebraic multigrid. So there's two basic flavors of an algebraic multigrid preconditioning. There's your classical or Rügi-Stüben, which is based on choosing finding course points. And then there's the aggregation family, or the smooth aggregation family, which is based on agglomerating nodes together. ML provides that second family of methods. They're similar. They do a lot of the same things. There's certain advantages and disadvantages to each family. Smooth aggregation, for instance, tends to be better at elasticity problems than classical Rieger-Steuben does. It tends to generate cheaper preconditioners, but they take more iterations than a kind of classical AMG. So, it's what's right depends on what your problem is. It also provides some domain decomposition capability. When we say it's critical technology for scalable applications, at the end of the day, if I want to run something really large, I need a preconditioner that's going to get my Krylov method to converge in some bounded number of iterations, regardless of size. And multi-level methods are kind of one obvious way to do that. Something at incomplete factorization will almost never do by itself. Normally, we use this kind of with petra to take an petra matrix to ML. But there kind of is a completely independent interface. For instance, Petsy uses to allow their users to use ML under the hood that uses a completely independent interface where it's just ML and none of the rest of Trilinos. This is a SQL package called Mulu, which is under active development. That should hopefully be released in a couple months. Again, it's supposed to provide the next generation capability to allow for advanced architectures, complex support, et cetera. If you're interested in eigen problems, there's Anisazi. Again, it kind of tries to break away the linear algebra objects from the algorithm to avoid a reverse communication interface, which reverse communication is incredibly general, but it can be a little tricky to program, especially if it's the first time you've had to deal with it. So it's an interface decision to make it a little different from ARPAC. Again, provides advanced architecture support. It has block eigensolvers, so if you need multiple vectors at the same time, it can do a reasonably good job at that. And a number of different algorithms. So it's got like your block Krylov Shor, kind of like what's in ARPAC, but also Davison algorithms, LOB-PCG, et cetera. And it can solve both real and complex problems. So it gives you a reasonable amount of eigenvalue capability. You can also use all the preconditioners that I've just discussed. So you can use your ML, your Ifpac, your Amethyst, what have you, to get those solutions quickly. On the top of our solver hierarchy, we have our nonlinear solvers. So I've solved my linear problem, and now I need to do it again. And so Knox provides that capability. So you've got, kind of your Newton's method and its variants like Broyden's method to that. It's got a number of different ways of dealing with Jacobians. So sometimes I write out a Jacobian and I have it in explicit form. Other times I might not. I might just have a function evaluation. And I don't want to go through the trouble and hassle of writing out a Jacobian matrix. Well, there's a couple different ways it can handle it. There's straight out finite differencing. There's kind of graph coloring, which is a sort of more intelligent finite differencing. If I know what can talk to what, I can use fewer vectors to do the difference. Or I can do a full-blown JFNK. That's kind of where I prefer to roll. Again, it's parallel and it operates independently of the linear algebra package, so you could glue in Petsy under the hood if you wanted to. So you can do kind of whatever you will to kind of meet the problem you have. Basically, to use this, and hopefully if there's some interest, I can go into a little detail in the hands-on section. You have to basically write a little wrapper for your function evaluation for your application to be able to call Knox. And it's a little tricky the first time you do it, but it's easy enough once you've seen it. There's also LOCA, which is for continuation algorithms. And to be honest with you, I don't know that much about continuation algorithms. But effectively, this allows us to handle both kind of continuation in its regular sense, but also do bifurcations. And so it's a nice kind of advanced capability that can be quite useful in certain circumstances. Finally, I can do optimization. So Mucho and Aristos are two packages we have to do that. There's also a kind of successor under development called the Roll, which is not released yet. Again, it's some optimization capability for folks who want to do that sort of thing. And finally, we have our kind of interface layers. So Stratamikos and Piro. Stratamikos for linear, Piro for nonlinear continuation sorts of things. The whole idea is it's a uniform interface. So I could go and learn the interface for Aztec and Bayless and ML and Ifpac, and they're all similar, but not quite the same. Stratamikos, and then Piro for the nonlinear, provide a way of unifying that. This works through this tethos parameter list guy. And the cool thing about it is you can basically capture all this in an XML file. So let's say I've got a code that's going to solve a variety of problems, some of which, maybe they have the same physics, but some of which are easier and some of which are harder. Maybe it's the mesh. Maybe it's the materials. Who knows? I want my user to be able to basically choose what solver they want to use. OK, I want to do a different set of things for the hard problem or the easy problem without having to recompile my code completely. So I could write my own input processor for it, right, and build my own input deck methodology and write out my own options and build my own parameter list. And some applications take that perspective because it generates a unified interface for my code. For other applications, especially applications that you're not expecting a whole lot of other people to use, you want to make the interface simple, but not like bulletproof. The idea of being able to specify just the Trilinos options from an XML file. XML, I have a collaborator who says XML is viewable by robots and not people, which is true, but it's actually not so awful even for people. And if you add an interface like Optica to it, it becomes very easy to access for people. And so basically, you can specify your solver options through an XML file. And Piro does the same thing for a nonlinear one. So this is a bit of a kind of walkthrough for what one of these might look like. Don't worry about all the particular details of each line, because there's a lot of them and they're hard to read. But basically, sort of the top level, I say, here's the linear solver I want to use. Here's the preconditioner I want to use. So you kind of just specify those in an XML framework. If you have a good colorizer in like Emacs or Eclipse, this can make these fairly easy to read. Then I create a bunch of options for linear solvers. I say solvers plural because I could have several of them. I could say, well, here's what I want to do if I want to run mumps, or here's what I want to do if I want to run Aztec, or here's what I want to do if I want to run Bayless. And I can list all my various options in the file, and then just basically go right all the way up to the top and pick which one I want to use for my particular problem. Likewise, I can do the same thing for a preconditioner. I could say, I just want to use Ifpac, or I just want to use ML, and then specify at the top which one I want to use, enabling you to kind of at runtime pick the solver methodology you wish to use. Quite nice and convenient for sort of research applications. All the sublists are passed to the code, and they're all validated. So if you type something wrong, which I do frequently, the code will barf early on and say, hey, I have no idea what this option is. You should fix it. Rather than running 3/4 of the way through your code, hours later it crashes and you have no idea why. It crashes earlier, and hopefully with the message that tells you, hey, this option's wrong. Here's a list of what you could have had. I have no idea which one you really meant. So it's easy enough to fix. And they kind of crash early, crash often fashion. So that's a kind of whirlwind through the capabilities. Now, if there are any questions about one of those, I can take them now. Otherwise, I can talk to the how you would actually get started with Trilinos part. Yeah, we're doing plenty fine on time. What? Yeah.
Have you ever done any performance comparison? Because you have something that has also maybe higher, also have
Yep, absolutely. So as a general rule, I'll speak about the hyper team because I know most of them personally. We're loath to do like purposeful bake-offs because to do them right and fairly takes a lot of time, especially with things that require tuning. It takes a lot of time to be able to generate fair comparisons between method A and method B. Because you use the defaults, they're not always right for every problem. And the defaults for one package are going to be right for different problems than the defaults to the other. So folks generally try not to do that because it just soaks up a lot of time to do it right. Because if you find out your package is losing, you're going to spend no end of time and effort to make sure it gets up to the top. More seriously, we do some performance testing. So some of the next generation stuff that we've been working on, effectively we've been benchmarking this against reference implementations of certain objects. So we've been tuning, for instance, the matrix vector multiplication in petra recently. We looked at it and we're like, gosh, this looks a little slow. So we basically baked it off against ePetra. We baked it off against kind of a reference implementation of how you do it using kind of a simpler object. And lo and behold, we found out it was slow. And so we're basically refactoring a lot of the code to improve its performance. I really wish the literature provided a better place to document these sorts of things than they do. And that's kind of to our discredit as the overall scientific community, that we don't provide as many really good places to document performance. I mean, yeah, there's a chart in a paper saying this was fast, but...
So can I add something? So,
sure, go right ahead.
At the very beginning, we used to have a lot of those performance metrics. And as I mentioned at the very beginning in my talk, is that right now what we've seen is that the functionalities that are implemented, like in the past, we used to compare a lot of the solvers, linear solvers in PETSI with Aztec OO. Mm-hmm. We don't do that anymore. And in reality, because the development, if you have a C++ framework, it's the time to development. And if you really need to access a specific solver or preconditioner that is not available in Trilinos, but is in PETSI, we have work on interfaces, to make that interoperability accessible to you. I also mentioned that, as Chris also mentioned, so it's very functionality specific. So I will sort of, in order to make the selection, I will focus more on what do the problem really needs, in terms of how successful these tools have been to scale to large number of processors. Both of them, interchangeably. One year you will see a Gordon Bell that has used Trilinos. The next year you will see PETSI. And it's not really that they are doing something to optimize the codes, but it's really how well you tune your parameters on the numerics. I mean, there's a lot of work that goes already in the implementation. I would say I will focus more on what framework is going to be more useful to make the selection between the two. But it's not that, like there's no new development added to Aztec OO to be able to do a fair comparison between the krillabs of spaces that PETSI had been, improving, and because Aztec has moved on, and you have now the Bayless package, as Chris mentioned, or the ML. I mean, PETSI doesn't spend much time doing the multi-grid because they know that the ML is a robust library and has been useful in the PETSI framework as well.
So it's more or less like it doesn't really matter. I can start with Trilinos or perhaps.
Right. So the idea is that you look at what functionality you really want. So so right now, because both packages or the three packages are precondition based, so look at what kind of preconditions they provide. The only thing that I will sort of add is that what we have noticed is that if the problem is very small, using some of the hyper preconditioners would require a lot of setup because they are really geared to large number, large problems, large number of processors. So yes, if you were to take a code and compare it to, you have a small problem, you want to compare that small problem with a PETSI or Trilinos, what you're going to notice is that it's extremely slow. But if you try to scale, for a large number of processes, then maybe the solution that you need. And also a lot of things are changing. It's not only the basic linear algebra, but there are a lot on the solvers so it's very hard to do a fair comparison.
Yeah. Well, and to add to that, I could almost guarantee you that if I really wanted to be sort of rude to my colleagues at Lawrence Livermore, I could create a set of problems where I know the ML algorithms will be better than Hyper. And they can do the exact same thing and pick a set of problems where they know Hyper's algorithms will be better than ML. It's just because they're different classes of algorithms. They're similar and they do a lot of things about equally well, but there's some things each is better at. And so effectively, pick a framework you think will address your issues, and then courtesy of some of the effort we have through Axe to get these software tools to play together better, you can try them, try both or all of the above on your problem and find the one that works best for you. Most of them will work reasonably well kind of regardless if you tune them correctly. But at the end of the day, if that much performance is really important, try them both and see which one works best. Feel free to contact the developers. I can speak for the Trilinos team. I'm sure the PETSI and Hyper teams feel the same way. If you have questions, ask. We'll be happy to sort of take your emails and see what we can do to help out. Any other questions capability-wise? Okay. So the how do I section. How do I build? How do I learn about the common Trilinos kind of programming idioms? Each package has a way it views the world, or each bit of software. What are the common ones in Trilinos? How do I find a Trilinos? And how do I find documentation? How do I find help when it doesn't work? So let's say you have an application, and you want to use Trilinos. Well, how do you get them to play together? Well, there's two ways. If your application uses CMake, Trilinos uses CMake internally, so you can just say CMake with the find package CMake, go find me Trilinos. And if there's a Trilinos either that you built yourself, or like on a bunch of the nurse systems, it's installed for you, it'll just pick it up. If you're using a kind of makefile-based system, we generate what's called makefile.exports, which basically give you all the information you want. So Trilinos first, it's a cross-platform build system, does similar things to AutoTools, but does Windows. And that's kind of one of the big reasons why we moved from AutoTools to CMake. You don't have to use CMake to use Trilinos. You have to use CMake to build Trilinos. But if someone built it for you, you never need to see it. If you do, find package Trilinos, done. And so the hands-on demo, there's an example script of that. I'm not sure who actually wrote the slides, but whoever did found it much easier than handwriting makefiles. That's a matter of taste. Oh, sorry. Makefile.export is another way of doing that. So one of the problems you get, especially with something that's this package-oriented as Trilinos, is you get link lines that look like that. And if I'm linking in 30-odd Trilinos packages, that's going to be incredibly long. And that the last thing I want you to do as a user is to have to write all that by hand. Because let's be honest, if I had to write all that by hand, I wouldn't use it either. And so makefile.export allows us to basically, it's going to create a variable, a make variable, that's going to have all the Trilinos link stuff in the right order. And then you just grab the variable and go. You can basically consistently use whatever compilers Trilinos used, that you used to build Trilinos, to make sure there's no compiler versioning problems. Likewise, you can be consistent with options. So for instance, if you're using like a checked STL, or you want to make sure you have MPI, that can all kind of come through. So to kind of hammer that home a bit, let's say I really cared about solving a nonlinear problem, which means I need Knox. Well, that's a linear system under the hood, which means I probably want ML, Ifpac, petra, maybe petra ext. I'm going to want to do a direct solve at the bottom of my multigrid. That means I might want Amisos. And I really want to use super LU. You can see how this turns into a disaster really quickly. There's direct dependencies and indirect dependencies several layers down. Managing that by hand would be somewhat suicidal, let alone if I wanted to add new stuff. Oh, I really want to use mumps as well. Oh, great. Now I have to go find out where super LU was in the link line and drop mumps in and hope that all works OK. Big pain. So either Knoxca has to do it itself, or we have to make you do it, neither of which is particularly attractive. So makefile.export makes it easier. How does it work? Let's say I really want to use ePetra. That's what I care about. So I basically just say, OK, wherever I stuck Trilinos, grab makefile.export.epetra, which will basically bring in the information for ePetra and anything further down the hood from there. That's where I installed it. Here's where I stuck the includes. There's variables for the compilers. I just say, ePetra, CXX compiler. What compiler, C++ compiler did you use? What flags did you use? You can grab them all right there. And then basically I have my libs at the end. OK, here's what I want. Then I just say ePetra libraries, ePetra TPL libraries, ePetra extra link flags. It's done. And so it now becomes fairly simple to actually write a makefile that handles all that. So you've taken this combination of lots of packages, and from the perspective of my application, all I have to do is that, and Trilinos is just going to work. It's a sort of nice way to do this. This is there's an example of this, makefile client ePetra, to kind of give us a look of how to do that. We also have a bunch of other sample kind of build scripts buried in Trilinos if you poke around, so you can see kind of how you'd use it with your application. All right. Software interface idioms. The idea, in a sense, is to provide a common look and feel up to some level for how things work together. So there's the lower level stuff, which is all in tethos. I'll go into some detail about that. This is really the critical one, the higher level matrix, the Petra model. And I'll spend a lot of time on that. And this is one of the key things to understand if you want to use Trilinos to do distributed linear algebra. It's also full of the key mistakes that everyone makes the first time they do it. I know because I made them all the first time I used Trilinos. And so there's basically a couple slides that when I was learning to use Trilinos, I basically printed out and just had on my desk. And every time I had a question, I looked them over and I'm like, that's how it works. I'll try to walk you through those. But if you are interested in using Trilinos, this is a very good place to ask me questions. But first off, the kind of lower level idioms. So parameter deck, we saw one of these for Stratomikos, letting us read this from ML. It's basically an associative list that I can build a hierarchy into. So I can have, as one of the items on this A list, I can have another A list. So the idea is you can build it hierarchically. OK, I have, say, my options for my solver. Below that, there's a preconditioner. Below that, there's options for sub-options, et cetera. You can do it from XML. You can also do it by hand. So if I build a list, I can set things, et cetera. I can get information out of the lists. Pretty simple. Or there's the Optica GUI if you have Qt built. You can basically set up a GUI that allows you to play with parameters. It's all reasonably straightforward in that regard. One of the other idioms is memory management. This is the whole idea of reference counted pointers. Certainly not a new idea, right? Java references effectively have this all built in from the get-go. C++ doesn't. And so you've got a number of options. Boost would be an obvious one. But partially because Boost wasn't reliable at the time, we wound up rolling our own, this tethos RCP, effectively allowing us to do reference counting on pointers. The most useful place this shows up is I have a matrix, say I want to precondition it, and it gets passed, OK, ML, have a matrix, and ML's like, oh, I need a smoother, Ifpac have a copy of this, but Amethyst have a copy of that, et cetera, et cetera, et cetera. So there's a whole bunch of people all pointing to the same matrix. Usually, that'll be OK. But sometimes there's concerns that it gets deallocated in the right order, and reference counting kind of makes that easy. There's a report on that you can get off our website if you're curious as to how our reference counted pointers work. They do add keystrokes. The downside, because it's not built into the language, I have to do extra work. So instead of saying like matrix star, I have to have a reference counted pointer of a matrix. There it is. The runtime cost is pretty low. We've actually tested that. One of the nice things about it is you can actually, our debug build can do range checking. So if you build up a fully debugged build, it'll range check your pointers for your arrays for you. Not every Trilinos package uses them. Some of the newer ones do. Some of the older ones don't. And it's part of some of the interface in there. And it can be useful in the right circumstances to make memory management easier. Time Monitor is another nice tool. A lot of times when I run a bit of software, I want to know how much each part takes, especially as a developer. So I know which parts to improve. Which parts do I need to pay attention to? And basically, Time Monitor is a way that does that. So it basically gives me a nice, scope-safe way of controlling a timer. And then at the end, when I'm done, I can call summarize. And basically, every timer of all the processors kind of condense. And now I can get min, max, and mean results on my timers across basically my entire parallel job. Now, nothing says that I have to use the same timers for the same things on the same processors. So in a Krylov method, for instance, everyone's more or less doing the same thing at the same time. But not all applications feel that way. Different processors might be doing different tasks. And so the time monitor will work just fine in that use case as well, where you're timing different things on different processors. Although that's not usually the way it's used, it works just fine. All right. Petra object model. This is the kind of key idea that underlies all of our linear algebra, and it's important to get right. So basically, there's two bits before we can actually get to something interesting. First off is a communicator, and the second is a map. The communicator is effectively an object that describes who I can talk to. So serial comm is an obvious one. I can talk to myself because I'm in serial. It's kind of a trivial thing. An MPI comm that wraps, say, MPI comm world is another obvious one. I can talk to everybody. But you can also do it to wrap all sorts of other MPI communicators. For instance, I might want to wrap MPI comm self. Yes, I'm an MPI job, but this really object is local. Or some MPI subgroup. If I have a subgroup corresponding to, say, my node on a multi-node, some multi-core machine, and I only want to do an algorithm that's local to my node, I can basically wrap that in a communicator. Or I wanted something at only one core per node, but there's one core in each node that has it. I can basically wrap up any kind of communication pattern I want. This describes who I can talk to. Now that I've figured out who I can talk to, the map describes how the data is laid out. Typically, a map gets used by a bunch of different computational objects, because in a lot of cases, we'll have objects with the same layout because we want them to be able to work nicely with each other. Maps can either be one-to-one, or they can overlap. Right? I can have a nice even partition. Okay, I get the first 10, Tony gets the next 10, et cetera. Or we can actually have overlapping maps. And those become incredibly useful when we think about data migration for matrices. Also, if I have two maps, that defines a way of moving data between them via like an import or an export. There's an object that if I hand it two maps, can allow me to move data between those two maps and how they're distributed. Finally, I get to objects, so matrices and vectors. That's kind of the sort of high-level semantic. Again, there's E petra and T petra. Oh, yeah. That's our picture. That's the Petra temple that we managed to decide is the symbol for all things Petra. Yeah, there you go. OK. What does this really look like in practice? Well, it looks something like this. I have a program. I call MPI init because I'm running MPI. So there you go. I've started up my MPI. And then I build a communicator. In this case, it's an MPI communicator. And I want to use MPI comworld because I'm not doing anything fancy. So there you go. I defined a communication object that says, OK, everyone's going to be able to talk to everybody else. Then I'm going to build a map. In this case, I want to have the same number of data objects per processor. So I say, each processor is going to have 1,000. I don't know how many processors I have. It doesn't really matter. So I say, well, OK, each processor have 1,000 with this communicator. And then it'll figure out, if I want to know how many elements there are overall, I can say, hey, I know each processor has 1,000, but how many things do we have in total? And it'll figure it out for me. Oh, that's kind of nice. OK, now I might want to build a matrix. I'll go into more details about that later. So a matrix has to have maps associated with it as well. It actually has 4 of them, but we're only going to use 1 for the moment. So I say this map, and I say, OK, I have a matrix. It's tridiagonal. Here's my map. And since I know how many elements I have, I can then go through a loop. I can say, OK, well, what's my global row ID? Effectively, what I'm doing is I'm asking my map, who owns this? Or what's the ID of this guy? Because I know I own it. Say my local I is going to be ID 4,621. I do my one less, one more, making sure I don't kind of run off the edges in either end. And then I take the matrix and I say, insert global values. Here's the global row. I have one entry. It's -1. That's the row it goes in. Or I have another one. It's 2, et cetera. And then when I'm done, I basically told the matrix, here's an entry, here's an entry. I can do this much more efficiently if I say, here's a row, here's a row. But for this example, here's an entry, here's an entry. Then when I'm done, I say, OK, I'm done. I'm done filling the data. And then what it'll do is do kind of its translation to a sort of efficient format. To make a vector, I say, I have 2 vectors. They both have the same map. Say I want this B vector to be random. Say random. Fill it with who knows what. I can control that by setting the random seed beforehand. But for this example, I've skipped that. Then if I want to say solve this linear system, I say, OK, I want to build a linear problem. A, X, B. Here you go. I want a solver for it. So I say Aztec OO. Aztec OO, have a problem. Takes a problem. And then, OK, how do I want to precondition it? I say, all right, I use Jacobi, please. And then solve 1,000 iterations with a tolerance of 10 to the -8. And it does that. And then at the end, I can basically report information. Say, how many iterations did you take? What's the residual norm? Wrap it up with an NP finalize, return 0. That's solving a linear, building all the communication stuff, building a linear system, and solving it kind of in a very, very simplified fashion. If I wanted to make this serial rather than MPI, let me do this again. There's the MPI version. There's the serial version. The only things that changed are up here. I just build a serial communicator. And down here where I don't need to call MPI finalize. Other than that, I just basically wrote serial code that works just fine in MPI. The tricky part is making sure you get this right with the global and local IDs. But if you do it consistently, your serial code works just fine in parallel. For those of you who like kind of UML-like diagrams, here's the UML-like diagram for the Petra object model. I'm not going to go through it in too much detail, but I'll give you the fast version. First object is a communicator, so it's the abstract interface to your parallel machine. Shamelessly mimics MPI because of kind of when we created it. And so the nice thing is it kind of limits our MPI dependence to ideally more or less one place. Because we use MPI everywhere, being able to kind of limit it to one location is convenient. Allows us to do a trivial serial implementation, which I just showed you. And it allows us to do kind of crazier parallel things if we need to, because it's all encapsulated in an object. We then have our distributor, which is also kind of a cousin of our maps and communicator, allows us to do sparse all-to-all communication. So one of the obvious things is gather scatter for OS processor values when I do, say, a matrix vector product. Go into more detail about that. Overlapping Schwartz, redistribution. It's all related to this import-export idea, saying when I have two maps, I can define a way of moving data between them. What they call an element space really here is kind of what I'll call the map, describes how we lay out distributed objects. For vector, it says which entries are on which processor. For matrices or graphs, it says which rows or columns are on each processor. And in Petra and T-Petra, that element space idea is a map. All of our distributed classes are based on a common distributed object, which gives us the communication kind of built in under the hood, and everything derives from that. We have dense matrices and vectors, which are plausible and Ifpac-able locally. And then finally, we have graphs, which specify the non-value portions of a matrix, which allow us to use all that pattern-based load balancing, for instance. Then finally, matrices. Allow us to put it all together. We can now redistribute those. And I'll go into a bit of detail about how that works later. So that's kind of the model quickly. Now for the fun part and the hard part, going through maps. So we have this other idea called block maps, and I will not talk about those at all, because maps are actually complicated enough. And if you're interested in T-Petra, all the ideas are the same. It's kind of core to the Petra object model. I'm just using ePetra to explain that. So let's start with a map. So a map can be one-to-one, okay? AKA each global ID only appears once in the map on a single processing element, core, what have you. There's no overlap, okay? Certain data redistribution items are going to require one-to-one maps. For instance, with an import and an export, the way we set up our capability, certain directions have to be one-to-one. The other one can overlap, that's fine, but there's certain directions that are going to have to be one-to-one. And for a 2D object like a matrix, these two maps, these domain maps and range maps, which I'll explain in a minute, also have to be one-to-one. So this is a slide I had on my wall. This is the four maps for a matrix object. And so basically every matrix object is going to have four maps associated with it. Two of which I think of as more kind of implementation, and two of which I think of as more mathematical. The mathematical ones are the last two, the range map and the domain map. And so why I say they're mathematical is I think about it as I would think about an operator. An operator has a domain. An operator has a range. The domain map is the map of things the operator can operate on. The range map is the map of the result. Okay? So if I have a matrix A, the X vector, or multivector as the case may be, is going to have to line up with my domain map. Because my operator is only allowed to operate on things which match its domain. Likewise, the Y vector here, if I'm doing A times X equals Y, is going to be its range, because that's what the operator puts out. It has a result that's its range. The other two are kind of the under the hood sorts of things. The row map and the column map. So the row map is a list of rows I own as an operator. That's a kind of internal thing. It might be the domain map, or it might not. Usually it is, but there's no reason that says it has to be. The column map is the other one. It's the map of columns that each processor owns. This is the hardest of the four, because these two are relatively obvious. This one's usually the same as that one. Column map's the hard one, because the column map is the one that almost always has overlap in it. And the way to think about it is this. Let's say I have two processor entries, one of which has a certain part of a matrix and the other has another part. If I own the rows, I'll have columns that correspond to rows I own. But I will have columns that correspond to rows I don't own. And so thus, multiple people are going to have those columns. And so the column map's going to have overlap. I'll walk you through some more example of that in a moment. So here's our toy problem. It's a nice 3x3 matrix that I'm going to solve on two processors. There you go. It's 3x3 matrix with an x and a y. And I want to do a matrix vector product. Example number 1. This is the standard case. So what I have here is my first two rows of this guy here belong to processor 0. So these two are processor 0s. This row is processor 1. Okay? X and Y. First two rows are processor 0. Last row is processor 1. Nice and simple. All right, so processor 0 looks like this. Processor 0 looks like that. So what do my maps look like? Well, let's start with domain and range. They both contain entry 0 and entry 1. We're in C++ mode, so all counting starts at 0. My apologies to any mathematicians in the audience. OK, so I have 0, 1, 0, 1. Simple. Row map, 0, 1. OK. Column map, 0, 1, 2. All right. The other processor, domain, range, row are all 2. It just has the last guy here. But my column map, 1 and 2. I have an overlapping column map in this matrix because I have effectively communication between these two parts of the matrix. Roles are wholly owned. Row map is domain map, is range map, and it is 1-to-1. Column map is not 1-to-1. It's the hardest. That's the problem I had when I was first learning this, is trying to get my head around what a column map is and how it all puts together. But it's almost never 1-to-1, and this is a good example of a standard case when it's not. When I'm done assembling my matrix, I just call fill complete, which is going to make this assumption for me that row, range, and domain map are all the same. OK, so that's the standard way we interact with Trilinos 90% of the time. Let's get fancier. All right, let's do twist number 1. Here I'm basically messing around with the range and domain maps a little bit. So the difference here is the matrix is distributed the same way. The first two rows are processor 0. Last row is processor 1. Only I'm doing the domain and range map differently. So processor 0 is now going to have these two parts of the domain, but this part of the range. Processor 1 is these two parts of the range, but this part of the domain. So I'm basically, in addition to having this matrix do a matrix vector product, effectively it's shuffling who owns what. So that's a twist. So OK. Row map for this guy, 0, 1. Column map, 0, 1, 2. This didn't change from the last time. Domain is 1 and 2. Range is 0. For processor 1, row map is 2. Column map is 1, 2. Same as the last time. Domain map is 0. Range map, 1, 2. Our rows are still wholly owned, but our row map is not our domain map, and it's not our range map. They're all 1-to-1, but they're all 1-to-1 and different. Column map's still not 1-to-1. That's not a surprise, but it all works together. The kicker is when I call fill complete and say I'm done, I have to actually supply those domain and range maps. Because the normal assumption is the standard case that domain is row is domain is row is range. But if I wanted this particular layout, I could tell it so. And then it would take care of building all the data migration objects to handle that. Here's another twist. And this is kind of more fun. This allows me to do partially assembled rows. So let's say processor 0 has the first row of A and, say, part of the second row of A. And then it has the first Y and the last two X's. Okay, these guys are the same as the last time, but now I'm partially assembling rows. Each processor is part of a row. Likewise, processor 2, well, it's going to have the last row of A, part of the second one, and then the last two parts of Y and the first part of X. Okay, so what does this look like? Row map here, I have some of 0 and some of 1. Col map, I have 0 and 1. Domain map is 1 and 2. Range map is 0. Okay. Here, my row map is 1 and 2. Now, my row map has an overlap in it. Col map is still 1 and 2. Domain is 0. Range is 1 and 2. So I have a situation where my rows aren't wholly owned, and that should work for you. Row map is not the domain map, is not the range map. Range map and domain map are 1-to-1. Row map is not. Neither is the column map. And again, if I want to do this, I have to specify, OK, here's my domain and range. So those are kind of some of the twists from how we can do matrix things with petra. And so this is the tricky part. When I say it handles data migration, it's all about relationships between maps. So what will happen is it'll build what I call fill complete. It'll build an object that lets me move from the domain map to the column map. It'll build another object that lets me move from the row map to the range map. Because I'm going to need to do that under the hood. And this basically does an import or export between those two maps. And all that's built under the hood. So even if I'm storing this in this really funny fashion, as far as the rest of my code looks like, I just effectively see the domain and range. All the rest of the stuff is nicely encapsulated, and the data migration kind of happens underneath. This is the most important concept in terms of using the core linear algebra with Trilinos. And so if there's any questions about how this works out, what kind of crazy corner cases are allowed, please ask. Because I don't know about you, but this is where I wound up wasting a non-trivial amount of time when I first started, just trying to figure this stuff out. So any questions? Yeah.
For large matrix, how do you manage it? You do it manually, all these maps?
So for a large matrix, how does this get managed is the question. So normally what happens in a sort of stereotypical finite element code is somehow my mesh has been generated and partitioned. And so each matrix is going to own certain elements. OK? Oh, we have a microphone for questions. OK. Each matrix owns certain elements. And this allows me to basically derive some sort of ownership pattern for who owns nodes if I'm doing a nodal finite element structure. And so what generally happens is kind of like our little Aztec example we had earlier. We start off the assembly by saying, here's how many nodes I own. And maybe, if I already have global IDs I like, I say, here are their global IDs. And thus I build my initial map. OK, usually in most codes, that'll be the row map for the matrix. It'll also be the range map and the domain map, if my matrix is square. I'll basically keep them all in the same place. So once I've created one of those maps, courtesy of my discretization, I now basically can be able to, all the others kind of get generated automatically. So I just have to build the first one. Now if I have a case where I have a non-square matrix, so in like multigrid, a grid transfer operator, for instance, now I need two sets of maps. I need the map, effectively the range map and the domain map, to specify this object, otherwise it's not well posed. And then usually I'll let the row map be the range map in that case. That's how, like I said, the case one, was the 90% of the time context. 90% of the time things work like this, which means there's one map you have to manage explicitly. That being said, there are cases where you want to do some of the crazier stuff. Does that kind of answer your question?
Yeah.
Anybody else? Go ahead.
In the second twist, how's the row map not 1-to-1? What are you comparing it? I mean,
Okay.
What are you mapping to what? The row indices are mapped to that row map set, or? So
the row map is not 1-to-1. So look, the way to think about it is processor 0 owns this row and part of this row. It owns the -1 and half of the 1. So you can think about this as like a 1D finite element problem, right? On the left side, I have 1 minus 1. On the right side, I have 1 minus 1, which is where the 2 comes from because I add them. But let's say I only control the element that corresponds to this guy. That's why I only have a 1 there. The other one controls the last one, obviously, but only part of the middle row. It only controls, in this case, this is like there's two elements, right? The element connecting this point and this point and this point and that point. And I've broken it up with an element-wise decomposition. So each processor owns part of row 1. So they're listed as the row map having an overlap. Does that make sense?
Thanks.
I was going to say that's not normally the way I recommend handling finite elements in parallel, but it's an example of some of the crazier things you can do.
More crazy, like the TRIS3, TRIS4.
Oh, sure, absolutely. There are all sorts of crazy things you can do with that. Most of the time you don't need it, but every so often there's some time you need to do something really kind of wild. Generally, you can specify the column map for a matrix, for instance. You almost never want to do that because you will make a mistake. At least I will make a mistake when I do it, but there's like that 1% where sometimes it actually makes sense to do it. All sorts of crazy things you can do. But 90% of the time, case 1 is kind of where we live. Okay? Any other questions at this point? I can go on to fill complete. So fill complete. I've mentioned it several times. What in the dickens does it do? Well, it says I'm done with the matrix structure and then does a bunch of stuff. That's the fast version. Most importantly, it creates the data migration object. So if my column map and domain map are not the same, I'll create an importer. My row map and range map are not the same. I'll create an exporter. Those data migration objects under the hood that get built. Now, it turns out if I can actually get those if I want to, if I need to use them for another purpose. They're available from the outside of the matrix. You can grab a copy. Generally, there's a couple rules. First of all, the domain map and range map always have to be 1-to-1. And if my matrix isn't square, I will always need to specify the domain map and range map because I have no way of knowing effectively what the domain is if my matrix isn't square because I have no idea what size this thing's supposed to be unless I say it explicitly. The other thing fill complete does is kind of collapse into a more efficient data structure to allow us to kind of run matrix vector products effectively. So it basically takes this sort of intermediate data structure and drops it into a compressed sparse row. If you wanted to learn more about Trilinos, well, first off, there's the tutorial. So we've got a tutorial on our website. I think the 10.6 one's actually a little old. But there's a version of those slides up on the website. There's also documentation for each package that's in a public release. Most of that is generated via Doxygen, so it's effectively generated from code comments. There are several packages that actually do have their own manuals, ML, for instance, being one of them, that you can look through and see how those work. There's a Trilinos wiki on Google Code, which has a bunch of examples. Inside the source code directories, there's often examples for each package as well, some of which are on the Google Code, some of which are not. The examples in the packages are usually a little bit more exhaustive. We have mailing lists. So the most obvious one is Trilinos Users. It's open to basically anyone who's a Trilinos user. There can be a non-trivial amount of traffic on that sometimes, but it's a place to ask questions. If you don't know specifically who to go to, you can email Trilinos users and say, hey, I had this problem, or hey, I found this bug, or what in the dickens is going on here? You can kind of ask all those questions, and you'll usually get an answer pretty quickly. If you wanted to have a user meeting or a tutorial, well, we're at the Axe workshop, right? We can get a Trilinos tutorial right here and right now. We also have a Trilinos users group meeting every November. It's usually the first week in November, occasionally the last week of October, in Albuquerque at Sandia. It's a meeting and a tutorial. So the first day we'll have a tutorial much like this, plus like a hands-on section at the end. And then afterwards, there's a number of user days where we have developers talking about kind of different developments and packages. The capability area leads will talk about, hey, here's overall what's new in like eigensolvers and linear solvers or whatever, and then different developers will go through different packages. We usually also have a couple of users highlighting their experience with Trilinos. So if you have an interesting Trilinos story you want to tell, certainly talk to us, and we can see about getting a slot at the Trilinos user group meeting. And that's both a good story, hey, I used Trilinos to solve my problem, or a bad story, here's where I got stuck because of X, Y, and Z. Here's things I think you should improve. Talks are available both in slide and video form over the last several years. We've got an archive of those, so you can go look at them online if you so desire. For our European collaborators, we started last year, earlier this year, the Euro version of the Trilinos Users Group meeting. It was at EPFL Lausanne in Switzerland. We had a number of European users come there, and several developers go to be able to talk about how they're using Trilinos in a fashion that's a bit more convenient than having to fly all the way to Albuquerque from Switzerland, say. To get Trilinos, well, you can just go download it. Again, off trilinos.sandia.gov. It'll be a big old tarball of the source coupled with a whole directory of sample build scripts, so you can start with one of those and modify it as you see fit. The nurse machines already have Trilinos installed on it, so you just do module load Trilinos, and you're golden. So depending on the package, they're either LGPL or BSD licensed. So if there's any licensing questions you have, I know as a graduate student that probably doesn't come up too much, but if you're working on like a commercial code, companies sometimes care about licensing arrangements. You can email us to find out more details, but each package should be marked as to how it's licensed, be it LGPL or BSD. Building it, you need to get a copy of CMake to build it. At least version 2.8, cmake.org, go download one. You're also going to need an LA pack and a BLAS. Most systems will have a reference implementation on them. The Intel MKL, for instance, does a pretty good job. Atlas is always a good option in terms of kind of auto-tuned BLAS and LA pack. Find one. Your system might have it, or you might build your own. An optimized one will give you much better performance, and there's just no question about that. You're also going to need an MPI. Pick the one you like. We can work with OpenMPI, MPitch, etc. For some computers, there's going to be a bunch of options installed on them already. So for instance, the nurse machines have a whole slew of different MPI varieties. Pick the one you want. Or in the case of the nurse machines, pick the one that they built Trilinos with. Many other third-party libraries. SuperLU, for instance, is something a lot of users will want. You're going to have to download those yourself and make sure when you build Trilinos, Trilinos knows where to find them. You're going to have to write a short configure script. I highly recommend actually writing it out and saving it in a file rather than trying to do it by hand, and then the next time you need to configure, remembering what you did. There's a whole bunch in the sample scripts directory in Trilinos. Probably the best thing to do is find the one that looks closest to the sort of machine you're building on, and then start tweaking it. Oh, I didn't want this package, but I do want this one, or what's that option? Let me get rid of it and try to see what happens. For those of you who've never used CMake, the overall procedure has an AutoTools-like feel. You do a configure script, the analog of /configure, but it basically runs the CMake configuration, make. If you want an installed version, make install, or make-j, whatever, however big your machine is. It might work, it might woof. You can also turn the tests on if you're concerned about how it built and run through all of our testing if you want. There's a Trilinos CMake quick start on the website that you can use to kind of walk through. And you can ask me at the hands-on if you're interested. I'd certainly be happy to talk through if you're looking to, once we get through the actual content I need to do, if you have any questions about building Trilinos on your own machine or whatnot, we can talk about that afterwards. For the hands-on tutorial, okay, so all the examples I'm going to use are off our Google Code. I'm going to sort of walk through the ones I like the best, but if there's particular examples you want to see, please let me know. I will be happy to do them. If there's particular packages you're interested in, particular capabilities you want to see exercised, particular tweaks you want to see me make, I'm open to all of that. Example code's there. All of our examples actually work, as far as I know. There's the web interface to Trilinos. So the College of St. Benedict / St. John's University in Minnesota hosts our web Trilinos. Basically, it hosts the development branch, although we're actually going to use a release for our examples here. There's a username and a password for it. I'll give those out during the tutorial. And basically, it's a website with cut and paste your code in. There's a reason why there's a username and tutorial on that, because effectively, they're allowing us to run arbitrary code on their machine. So they expect us to be adults about that and not do anything malicious. And so it's a great way to play around, kind of to start off with how Trilinos works. All the nurse machines have it. And again, if there's interest and you have problems, we can help install it on whatever your machine is as well. Usually that's pretty easy, although sometimes you can get some library and dependency issues. especially if you didn't build your MPI, et cetera. All right. We still have about 20 minutes, so I have plenty of time for questions. I do have some more detail on some of the packages if you'd like, or anything else you would want. So I'll open up the floor to anything you want to ask at this time. We have a microphone, by the way.
So why don't we start by thanking Chris?
Oh, thank you very much.
Clapping always helps, before we know the first. So Chris, you had been working on the ML package?
Predominantly, I've been working on ML and then Mulu, which is its successor package, yes.
And are you going to spend some time this afternoon sort of talking a little
Well,
bit
I said I was going to pick the examples I really liked, and so
Okay.
ML would obviously be one of those. So my goal would be to basically do like a good example of a linear system with Aztec OO and ML preconditioning. ML is one of the packages with the user manual, and for good reason, because algebraic multigrid algorithms are very sensitive to parameters you choose. For good or for worse, that's just kind of how it is. Picking the right parameters for your problem are critical. And I can, for folks who are interested in that sort of thing, I can kind of walk through how I would go about choosing parameters that might be useful. I know I also work on an application code, and we teach a training class every year, and one of the parts of my teaching that class is how to use ML for this particular application. And so there's a set of things I always recommend users look at, and I would be happy to kind of walk through those for, okay, I'm running ML on this problem, and the performance is awful. How do I improve it? I'd be happy to walk you through that if that's something you'd be interested in. Okay.
Another aspect that I think is the extensibility. I mean, how can you build, on top of the ML preconditioner, your own preconditioners? And
so yeah, you can do, so one of the packages I didn't talk about in detail is a block preconditioning package called TICO. Because there's a lot of time that taking ML and just doing a multigrid isn't really what you want to do. And probably one of the best examples for a problem where people want to do something other than just multigrid would be solving Navier-Stokes. There's a whole literature of block preconditioners for Navier-Stokes. So like simple, if you've ever heard of it, or all of its variants, least squares commutators, pressure mass matrix preconditioners, et cetera. There's a whole slew of these things, of which you want to do multigrid on a part of the problem, but not the whole thing. And so what TICO lets us do is basically take this monolithic assembled problem, chop it up into pieces, and then, okay, I want to do ML on this part, or I want to build this approximation here, and then basically pick and choose the right preconditioners from Trilinos to do that. There are some examples of TICO kind of built in, like Navier-Stokes is actually, there's several examples for Navier-Stokes, but you can also use it basically to build your own. So, if you have a physics-specific preconditioner, for instance, you want to use on this block, but you want to use ML here and Ifpac there, you can actually build it in a framework to allow you to do that. It's a little tricky to do by yourself. Like the kind of examples they already have work very nicely and they're easy to use, but rolling your own is a little trickier. I've done it once or twice, but it can be a little challenging. Likewise, something else you might want to do, and we've done with, say, subsurface flow applications, is you might want to take a problem and do something very special on the problem you start with, transform it somehow, and then run ML beneath it. So one example where we did that had to do with discontinuous Galerkin discretization. So multi-level methods are generally designed for piecewise linear finite element, solving a Laplace problem. That's kind of where they score really big. And so we were solving a Laplace problem, but using a kind of discontinuous Galerkin discretization. And so we basically built a little wrapper on top of ML where we could start off and do something very special, do a very specialized grid transfer, and then everything below that was just kind of generic ML. And it worked quite nicely for that particular problem. So if folks are curious about how you would build on top of ML, I'd be happy to walk you through that as well.
I think that we have Matt in the room who has also built some stuff.
Oh, I'm sure. Any other questions?
How much do you know about the Anisazi so far?
I've used it a few times, mostly because I need eigenvalue estimates for something, but I'm certainly not an Anisazi developer or an expert about it, but I can try to field any questions. I just might not be successful.
I think Yeah. You had Patrick.
Okay.
And the other one is the Fortran interface.
All right, so Fortran 2003, first off, is what you'd need. So if you're just using Fortran 77, the right way to interface with Fortran 77 is to use C Trilinos effectively, and then basically do a Fortran wrapper around the C code. And so I've done that several times, although it's always a little tricky to get right. The Trilinos interface is a full-blown object-oriented interface, object-oriented Fortran interface. And so in theory, that should give you the exact same sorts of power and capability that you would have if you were using the C++ version. I haven't used it personally, mostly because all the Fortran codes I've worked with have been pre-2003. So I've been stuck with having to basically use C Trilinos or an interface like C Trilinos and kind of shoehorn it in a kludgier fashion. But if you're using the newer Fortran, if you have a modern Fortran code, using like a newer version of Fortran that should work straightforwardly. The developers for that are actually at the Sandia, California. So I'd be happy to put anyone in touch with them if there's any questions about using that. Damien Roussan, Carla Morris, well, she's not really at Sandia, California, and Nicola Master. Yes?
This may be a dumb question.
There are no dumb questions, although I might give a dumb answer.
If you're working with two different codes, one that functions on C++ and another that's using Fortran, and you're trying to combine them, one's row major and one's column major, I'm just wondering how Trilinos would handle that.
Okay, so, yeah.
That's a great question because that's what happens in many of the interfaces.
Yeah.
So there's two ways to kind of just think about that. One of the simplest ways to, if you're willing to allow Trilinos to own your matrix, then this isn't as much of a problem, because you can basically give Trilinos the data, and the order you give it the data will affect how efficient, say, the matrix fill is. But if you're willing to let Trilinos own the data under the hood, then you can basically kind of use it interchangeably either way. If your application is really owning that data and you're trying to basically build get Trilinos to use the application's native data structure, that gets a little more complicated. Because effectively what you need to do is take your native data structure and kind of put a little wrapper around it and say, this provides the functionality that Trilinos would want. And there's actually a mechanism for doing that, to be able to provide that. That wouldn't be the way I would go about doing that, especially if I have like a Fortran column major code. I would rather effectively, whenever I'm filling my matrix, just call Trilinos and say, here you go, have some entries. Here you go, have some entries, and let Trilinos own the matrix under the hood. Would probably be the cleanest way to do that.
What about the CUDA?
Okay, so for what I'll generally call advanced architectures, but specifically for GPUs, our sort of second generation linear algebra stack, so Cocos, Petra, et cetera, and then the preconditioners that build off of that. The goal is to have that entire thing able to use CUDA, cuSparse, cuBLAS, all the various other NVIDIA-related packages. For the basic core linear algebra operations, it's there. So Petra and Cocos will allow you to basically run matrix vector products on a GPU and methods that build directly on that. You're going to have to basically get that all to link appropriately, but I don't think that's hideously hard. But that all works. So in terms of getting all so they'll all work. Bayless will work just fine because that's completely templated. The preconditioning we're still working on. So especially in terms of incomplete factorizations and multi-level methods are something that's still under development for CUDA. There's been some really interesting developments in CUSP, which we also have an interface to out of Illinois. We've been talking with Steve Dalton extensively this summer about being able to interface parts of that in Trilinos as well, so we can use their work effectively under the hood. But that hasn't kind of reached the point where we're ready to release it yet. So yes, CUDA, yes, but not as well as we would like, and we're working on it.
Do you have users that are actually explaining?
At Sandia, no. But at Oak Ridge, there are some people who actually are using Trilinos on CUDA.
How did they
Their problems are easy enough where diagonal preconditioning suffices. You're solving a mass matrix, right? It's easy enough to do. But yeah, for a real problem, that's just not going to cut it. I agree. And so that's why we're working on effectively getting that through. And we're just not there yet, unfortunately.
Right. So any more questions? Okay, so then we are going to take a break now, and we will reconvene at 11.
All righty. Well, thank you very much for your time.